Having successfully authored your clearance toolpath, we can now move forward to the roughing toolpath. While the clearance toolpath had the aim of removing as much material as possible in a short amount of time as possible, the roughing toolpath is the intermediary step so as to make sure that your final finishing toolpath can effectively mill and define the final surface of the model without having to engage in too much material. An example of this is that having used a very large 16mm ball end mill to remove as much material as possible, we now use a flat end mill to remove the scallops left from the ball end mill of the clearance toolpath and come as close as possible to the actual model while still leaving a sufficient margin for the final toolpath to define the actual surface. The aim of the roughing toolpath is to minimize the amount of material that the finishing toolpath has to engage in, so as to make sure that the finishing toolpath, which often uses a tool of a relatively small diameter, can properly define the final surface texture without hiccups. One thing that we have to take into account milling plywood is that plywood when milled leads very easily to frizzying edges. Since it is not a solid wood, there are very thin layers where each individual layer may deteriorate. Thus, it is important for us in this example, milling plywood, that we use a downcut tool. That means if we change to the tool library in the Google Drive folder and open this photo overview again, we can see here, zooming in on these two on the second row, that usually, or in most cases, in the case of upcutting tools, the flutes of the tool rotate in such a way so that when the tool is rotated in a clockwise direction, the flutes move upwards, which means that the material that it engages in is removed by a force that is both lateral as well as vertically upwards. This is very good in most cases, because it means that the material gets properly extracted upwards and can get sucked away by the dust extraction and not get stuck down in the material. But in some cases, such as when milling plywood or these thinly laminated sheets where each individual layer may deteriorate very easily, especially when engaged in an upwards manner, we can use a down-cutting bit. We don't have as many down-cutting bits at KTH Architecture School as we have up-cutting bits, but the advantage is very significant when milling plywood and materials which easily leave frizzying edges. You see here that the flutes are spiraling in the opposite way as this is. And this means that when this tool, this down-cutting tool, engages in the material, it removes material both in a lateral way as well in a downwards vertical way. This is, like said, a disadvantage when it comes to the extraction of milled material. That which otherwise would have been more easily extracted by the dust extraction are instead pushed down into the material. But the advantage is significant when milling these thinly layered materials such as plywood, since it does not leave such a significantly frizzied edge. This tool in particular would be, if this is 8, 9, 10, which would be tool number 10. Since it is a 10 diameter tool, I deem it a very good candidate for our roughing toolpath. But let us first go to the tool library document and double check. Okay, here in the tool library we can Control and F and search for down, as in down cutting. And we see that there are 4 searchable instances of down, but we see that there are actually only 2 tools, since it is both stated here in the direction of cut column as well as the comments vendor column. So we see here that we only have 2 down cutting tools, and one has a cutting diameter of 4.5 millimeters and the other has 10 millimeters. And that was index 10, which was the one we previously viewed here. So I think that our candidate is given. And then we can go to the community feeds and speeds documents, and we can Control F, search for 10 perhaps. And here we see all the instances where this tool has been in use. So it has been used for bamboo wood, it has been used for birch plywood, very good, as well as for MDF. So we can enter a new index here, or a new index row, 44, author, run date, and we can copy the material here. We could have copied all the other except the index row as well. And we should copy the stock material thickness as well, since we're using the same stock, although in a succeeding toolpath. The bit that we use, the tool that we use, is tool index 10, which is a flat end mill of a cut diameter of 10 millimeters with 2 number of flutes. These are specific to the tool, so we can copy them from there. We can cancel the search here, having decided on this tool. Generally, when it comes to spindle speed and feed rate, if you use a smaller diameter tool, you should use a slower feed rate, and the spindle speed may optionally be increased if so necessary, but it can also be as a default or as a starting value, the same as the previous operation, as long as the feed rate is lowered, because this would yield a lower shipload per tooth. We can demonstrate this. If we copy the value of the previous toolpath, the clearance toolpath RPM speed here, and then we can perhaps decrease the feed rate from 425 to 300, which is a decrease of a little over 25%. We can copy this cell here, and we see that the shipload per tooth has been decreased, since we're using a slower feed rate while maintaining the same spindle speed. And the maximum depth of cut should also be adjusted down, so perhaps 2 millimeters. And copy the formatting of the above cell with Ctrl-C and Ctrl-Alt-V. And already there we have input some starting values for us to try out in Fusion 360. So here, with our setup activated, or the first toolpath here, it is optional which one, we add another adaptive clearing toolpath. This adds another toolpath, succeeding the first one here. And the first thing we should do is the same as we previously did. We should select a tool. And the tool is found in the KTH CNC library, product ID 10. And we just double check here that this is what we expect. We see that it is the downcut. We double check with the tool library. Very good. We select it. And now this has been previously demonstrated, but it is most important that after selecting the tool, you click again to select it again, but this time you do not alter the original in the KTH CNC library, but instead the duplicated copy in the document tools. So here we see here, product ID 10, this is the one we want to change, because you see that this also has a tool number of 1, which would lead to disastrous results should this not be changed. Then it would, during the actual milling, try to use this toolpath that we defined for this tool, but instead it would actually fetch this one, which would lead to terrible results. So, having this one selected, right click on it, click renumber tool, and renumber it starting from 2. And now we see here that this will change from 1 to 2, renumber. And now we see here that this flat end mill product ID 10 has now tool number 2. This will be put in tool holder number 2 in the CNC machine. Alright, select this one. And now you see that this changed to tool number 2, as well as here, tool 2, and now everything is fine and dandy. Alright, like we previously did for the clearance toolpath, we now do for the roughing toolpath. So we input the spindle speed of 13,000 RPM, 13,000, and we input the feed rate of 300. This is all we need to change here for the first tab. For the second tab, this is an important tip to save machining time. For the clearance toolpath, it is very important to remove all excessive material, so as not to leave material in the stock where it could be a source of collision between the tool that you use for succeeding toolpaths and the material itself. So for the clearance toolpath, it is very good that you mill away all excessive material. But here, for successive toolpaths, we can actually define a machining boundary and use a selection and use this edge here that separates the bottom margin from the actual model. And this means that the tool, the roughing toolpath, will only move and engage in material within this boundary. And this saves a lot of time, proportional to the amount of material that is left in the bottom margin top surface here. To make sure that the tool, which has a diameter of 10 mm and thus a radius of 5 mm, we can have an additional offset of 5 mm. If you see here in the tool containment, you see that the tool moves outside the boundary to mill within the boundary. So with this additional offset, we make sure that the actual model, excluding the bottom margin, is completely milled. Here it is important under rest machining that you change the source from setup stock to from previous operations. This will make sure that it does not mill again where the preceding toolpath already has milled away material. Going into the third tab, heights, we can leave these at defaults. They are adequate. We go into the fourth tab, passes. We can change the tolerance from 0.1 mm to 0.5 mm. Here we change the direction of the milling from climb to conventional, and this is because we're using a 10 mm in diameter tool, and thus it is more susceptible to deflection than the 16 mm tool, and thus it is a prudent thing to be on the cautious side and have it be milled conventionally, so as to reduce the amount of deflections. Deflection can lead to micro vibrations, and micro vibrations can lead to the tool getting loose from the collet, and that is something we want to avoid. The maximum roughing step down here can be 2 mm as we defined in the Google document. And the fine step down here, that is what defines the final outcome when it comes to the thickness of the steppings after this toolpath has been completely milled. And as previously stated, the algorithm states 10% of the maximum roughing step down. This is 0.2 mm, is a very low value and will yield a milling that takes an awful lot of time. Here perhaps a fine step down of 1 mm is sufficient. This means that the tool, when moving in the toolpath, it will engage in up to 2 mm of vertical engagement in the material per pass, but then it will make sure, having moved downward 2 mm and engaged in the material at that depth, it will move upwards 1 mm and engage in the material at that layer as well. This means that the final result is a model that has vertical stepping of 1 mm between layers, but it will engage in a maximum of 2 mm so as to remove material as efficiently as possible. The stock to leave here is quite important. Since we intend to have a finishing toolpath, we need to make sure that the finishing toolpath has enough material left to mill away so as to actually engage in the material. And thus it is important to leave axial stock 1 mm. The radial stock to leave can be left at 0.5. Such a small margin will not put too much of a strain on the final tool for the finishing toolpath, but we need to leave 1 mm axially, that is in the z-axis, so as to make sure that the final toolpath actually can engage in that millimeter so as to define the final surface. We can go to linking, and then once again we can change the no engagement feed rate to 1200 millimeters. Alright, and ramp type can be left at default. And we verify these settings, make sure that it is number 2 and it is correct tool. 13,000 RPM as prescribed, 300 millimeters cutting feed rate, very good. And here we have this boundary, as well as an additional offset of 5 millimeters. The rest machining is from previous operation. Very good. Heights are as default. Passes, here we have adjusted the tolerance to 0.5 millimeter. Direction is conventional, 2 millimeters maximum pass depth and 1 millimeters final step down. And a little extra axial stock to leave. Very good. We can click OK to confirm these settings and it will generate a toolpath. And since this is rest machining, remaining stock machining, this toolpath will heavily travel, or it will travel very much. It will skip those areas where the clearance toolpath already has removed, but this is still a more time-effective way to mill a model than to allow the 10mm tool to mill the whole model in such a way. Alright, with the toolpath properly generated, we should inspect it in simulation mode. And one important thing to note here is that if you have only one toolpath selected and you click simulate, then it will simulate only that toolpath. If you have setup selected, it will simulate all toolpaths. But generally, when you work with toolpath authoring like we do now, it is good to simulate each toolpath individually, sequentially, and then when you are 100% sure that these are the toolpaths that you want to export, then you can one time more simulate the whole setup, so as to make sure that everything is according to your expectations. The first thing we should do is go to Info tab and scroll down here and check if there are collisions. It says that there is no detected collision. Very good. We can go to the statistics and just take note of the machining time and the machining distance. And then we can go back to display and display the toolpath, and then make sure that the speed here is not set to reverse mode as it was previously set, but actually to forward mode. And then we can start a simulation. As you see, when we simulate the second toolpath here and using rest machining, we already have the results of the preceding toolpath as a starting point. Now we can start a simulation. And we see here that it made travel, and then it made lead in, and then it makes engagement. And this is not a problem for this toolpath, but we can also, here in this view, we can disable the visibility of the actual model. Now the only thing that is actually showing is the base plate here, but when we hide this, it is invisible. It will be more clear for the final finishing toolpath. We follow the movements, make sure that you get a clear understanding of what it is doing. And here we see here that it first engages in 2 millimeters of the material. And having done so, it goes upwards 1 millimeter and mills away that millimeter as well. So it first engages in 2 millimeters depth of material, and then it defines a final result of 1 millimeter vertical layering or steppings. Very good. Having gotten a grasp of this, we can increase the speed. And like you see, there are a lot of travels. And while travel time is not lost time, but travel time is not active milling time, one might feel that it's a very ineffective way to mill. But it is still more effective than to try to use a smaller diameter mill to clear all the material in one go. But this is also something that you can experiment with. If you find that you only need to use one tool to get the results that you endeavor, then of course there is nothing that hinders you to make a one toolpath milling. But it all depends on the result that you want to get and in what time you can achieve that. I will increase the speed here, as well as disable the visibility of the toolpath. With the toolpath fully simulated, having made sure that there is no collision We can take the machining time and the machining... We can take note of the machining time and the machining distance and input these into the Google Docs document. So 5 hours and 19 minutes equals 5 hours times 60 minutes plus 19 minutes, I think it was. And the toolpath length was 141.281, 141.281. And we can copy the formatting of the above by Ctrl-C, Ctrl-Alt-V. And here we enter CAM. This is a 3D adaptive toolpath. This is conventional milling. We use rest machining. We have 0.5 millimeter radial stock left and 1 millimeter axial stock left. Very good. Very good. Now we have input all the parameters which we can as of now. Go back to Fusion 360. Before clicking close, we can export this stock preview by right-clicking on it, stock, save stock, save it here as tutorial, post roughing stock. Having done so, we can click close. Now we optionally can go into Rhino and import the post roughing stock. Okay. Make sure that we have a layer for it, post roughing stock, and assign the object to it. And now you can see if we hide the post clearance stock, we can see the difference between the two, the post clearance stock and the post roughing stock, as well as the imported model that we use. And just as a side note, if you decide that this is what you want as a final model, then of course feel free to omit a finishing toolpath and allow this to be your final toolpath. Then you can just skip to the tutorial where we export the toolpaths and export the first two instead. But since we intend to give this a smooth surface, we want to use a third and last finishing toolpath. Let's save this. Go back to Fusion 360. And now, having successfully authored the roughing toolpath, we can save the project. This concludes the 7th part of this tutorial series, how to author a roughing toolpath in Fusion 360.